to approximate certain functions. And we're looking at ones that we know one that is very close to the one we're looking for. All right, so let's try another one. Let's try, I say the radius of a circle is 3.04 inches. Estimate, let's say it started at 3.00 inches, and then it changed to 3.04. Estimate the change in area. So, all right, this one we are going to do in a similar fashion. We're going to estimate the change in area by doing f of x plus change of x equals f prime of x plus, f of x plus, get rid of that, the formula didn't have a prime there, it has it here, f prime of x dx. Alright, so estimate the change in area. So I'm going to indicate that I want the function. What is the function here? Since it's area equals pi r squared. Alright, so in this case the area equals pi times 3 squared, or area equals 9 pi. Alright, so we are going to look at the function evaluated at 3. So the function evaluated at 3 plus 0.04. So that'll give us, the function is pi r squared, so we're going to get pi times 3 plus 0.04 squared. That is what we're looking for, an approximation. So we're going to take the derivative. So the derivative here, a prime is, oops, went off the area there. The derivative a prime is 2 pi r. So I'm going to come back here and under, I'm sorry, I forget, I keep thinking that's the derivative. It's the function evaluated at x. So our function is pi r squared, and I'm going to put in the 3. That's my f of x. Plus, and then the derivative of the function evaluated at 3. So we have 2 pi r is the derivative. So I'm going to put 2 pi times 3 times dx, and that's the change, 0.04. Alright, this should be a pretty good approximation. So let's see what we come up with. 9 pi plus 3 times 0.04 times 2 is 0.24 pi. So I end up with 9.24 pi. And the actual change in area, if you go back and you do pi r squared with just the 3 in it, and then you do pi r squared with the 3.04 in it, the 3.04 will give a slightly larger area than the 3 did, and the difference between the two is actually the actual one. The actual change in area is 9.2416 pi. So you can see that this approximation is very close. Alright, so again, this works very well when you're very close to a function that we can do quickly, but when we add a little bit, this is a good approximation. So I want you to see how to use that The other kind of differential problem involves this formula. So we'll keep that one on tabs for certain problems. And now another one. Alright, so we have seen dy dx can be written as f prime of x. But if thinking of this again as a very small change in x, I can actually use dx in an algebraic way. So I'm going to multiply through by dx. So I get dy equals the derivative times dx. Alright, so that dy equals f prime of x dx is the often used to approximate error. And here's what I mean by error. Suppose that we are measuring say that we're measuring a circle. And when we measure a circle, not a circle, we're going to do a sphere. So let me sketch it. So here's a sphere. And the radius, I'll draw in sort of like that. The radius of our sphere is 4 centimeters. But when we measure that radius, we are often off by plus or minus 0.01. So, keeping that in mind, that's just our human error, the use of our instruments, the use of our eyes, our human eyes. We're often off by 0.01, plus or minus. So, with that in mind, what would be the approximate error in the surface area? Find the approximate error when you calculate surface area of the sphere. So the surface area of the sphere is the equation 4 pi r squared. So with that knowledge, we can use this formula to find the error. And it's going to always be the derivative of the function d, in this case s, the surface area. I'll call it just s. It's easier to put in one variable after the d than two, so I'll call it s. So according to this, we're going to say ds equals the derivative of the function, which is 8 pi r, times the change, the error. This is representing the little bit that you can go up and back, and so that's the little dx, plus or minus 0.01. So the change in the surface area can be 8 pi r 0.1, and I multiplied that out. I get plus 1.0053, and when I multiply it with the negative 1, I get negative 1.0053. So putting those together, I am saying that the approximate error in surface area under these conditions is going to be plus or minus 1.0053. So that sounds like a lot, because that's like a whole, say this is it's centimeters, so that's a whole centimeter. Are you happy with doing a calculation with a sphere and finding that it could be off by a plus or minus 1 centimeter? Well, it's not quite as bad as it sounds, because when you do find the surface area of this sphere with radius 4 centimeters, it comes up to 201 squared centimeters. So since it's quite a large number, 201, plus or minus 1 isn't so bad. If it was like 20 plus or minus 1, I would say that's too much error. Let's not consider this in whatever we're trying to figure out. But with 201 plus or minus 1, I think that's reasonable. Alright, you won't really get this totally until you do some of your own. So I will give you an opportunity to do that. So have these written down and pondered upon, and that will get you halfway there. All right, till we meet again. Good night.